But now we're saying, if I give you a bunch of numbers, can you write down the nth term equation? Okay. Now, so the key challenge right here, it's, well, this is A1, this is A2, this is A3, this is A4. So the equation has to work well with the n. Now, if you look at these numbers, can you see the pattern among these numbers? 5, right? Plus 5. So basically, we would say, what can we do? So it's plus 5, okay? So, and the bigger the term number, okay, the more 5 we add to the number itself. So we say it's got to be a 5 times n, right? 5 times n, seems like it should be 5 times n. But we also need to address the very first number as well, okay? We need to address the very first number. So we say, let's just say this is a plus 7 to begin with. But then we quickly bump into a problem. If you look into this, what's the problem? Not the 7 minus 2. The problem is that if you put n equals to 1, what's the number? It'll be 12. So we're like, we need to make a little modification right here. So we don't want to add the 5 when n is equal to 1. So how can we make that modification? We say, oh, just do n minus 1. So that when n is equal to 1, you're not multiplying by 5 because you have a 0 times 5. Okay. Now, I want to show you here that there's a generic equation that you want to capture here. This is the generic equation. The D stands for the difference. Okay, D stands for the difference between the numbers. Okay, and because you don't need to multiply or add anything for the first term, that explains why you see an n minus 1 here. But now you always want to simplify the equation. So after you get the equation right here, so you want to multiply it out so that you have 5n plus 2. All right, so a little bit simpler. That would give you the nth term equation. Okay, but the generic equation, it's over there in purple on the right. Yes. Well, you need to know the generic equation so that you can write this specific equation a lot easier. You can figure it out, but it may take some time to figure it out. But if you know the generic, I mean, if you look at this is practically mx plus b. The d is like your slope, practically mx plus b. It looks a little bit different, but practically mx plus b. Okay. And then you look at the second one, you're like, what kind of pattern do we see here? What kind of pattern do we see here? You can see the numerator. What's the pattern in the numerator? You get added by 2, right? So you add 2 for the numerator. And what about the denominator? You would be multiplying by 2. Okay. So how do we describe such kind of relationship? Okay. So we say, well, for the denominator, it's pretty obvious that this is again A1, A2, right? A3, and so forth. And if you look at the 1, 2, 3, and 4 with the denominator, can you see a very intimate relationship? Like these numbers with the denominators. Can you see the connection? Now you look at 2, 4, 8, 16, 32. Simply. They are simply the power. 2 to the first power, 2 squared, 2 cubed, 2 to the fourth power, and 2 to the fifth power. So that's a kind of recognition you want to be very sensitive to. So 2 to the first power, 2 squared, 2 cubed, 2 to the fourth power, and 2 to the fifth power. Okay. And then for the numerator, so it's basically, well, based on what we did earlier, okay, they are different by a number of, by 2. So we can simply do this. Okay, the difference will be 2. The first term, it's 1. And they keep adding 2 for the successive numbers. So we can do this, and we can simplify it to 2n minus 2 plus 1 over 2 to the nth power. So so overall, it is 2n minus 1 all over 2 to the n power. So if you have this number, if you have this nth term equation, then you can find out whatever term that you need, and that will be essential. Okay, that will be essential for our upcoming task.